I am Nick Harbour. I work for Mandiant, or an incident response company. I lead the malware analysis team, so that's kind of my shtick, I guess, whatever. And this talk is about a bunch of stuff. I just updated the slide, no big deal. Kind of a PowerPoint ninja, if you get that impression. All right, here's what we're going to cover. Don't worry about the reverse engineering primer. Just going to throw out some terminology, make sure we're on the same sheet of music. But if you're here for the more technical, nitty-gritty details and stuff, there will be copious assembly code in the slides, and C code and Python code. But you don't have to understand any of it, really. I'm not just going to go straight through that and leave you with nothing. And of course, there will be a tool demonstration at the end and whatnot. It is certainly prototype / proof of concept, whatever. So don't go download it right after this and start shooting me bug reports, because chances are, yeah, I know it's got bugs, but whatever. Anyway. So reverse engineering primer, we split reverse engineering in general into two main categories: static analysis and dynamic analysis. Static analysis, of course, being anything that doesn't require actually running the code, and dynamic analysis being anything that does involve running the code. So the techniques we're going to be talking about here is all about doing better dynamic analysis. I don't have any source code analysis techniques or anything like that. It's all just about letting the binaries run and being able to observe their behavior in a better way. I still got a lot of newcomers. Yeah. All right, current approaches to the dynamic analysis. A lot of network monitoring stuff people are doing, a lot of really creative solutions for that. There's hardware emulation, which is pretty popular, usually kind of expensive though. You're in the tens of thousands of dollars for good working solutions. And really, there's nothing I'm going to be presenting here that those products probably don't do better. But $10,000 always does better than no dollars, probably. And kernel level monitoring, this is what we and my company use extensively, because we don't normally pay $10,000 for tools. So we have tools like sysinternal's process monitor, which we use to do pretty good dynamic analysis, behavior analysis on a running process. And I'm going to be comparing and contrasting the techniques I'm going to be using here to monitor processes with, primarily with that tool, and showing where its kind of weaknesses are and where potentially down the road we can be with a better approach. And of course, debuggers. Inevitably, throughout the course of the talks about what I'm going to be doing and sandboxing and all that stuff, people are probably going to be wondering, well, why can't you just do this with immunity or whatever? But you are always operating as a debugger, even if you want to play in that cat and mouse game of anti-debuggering and participating in that. So I'm trying to come up with a solution to not act as a debugger at all, just to do straight process injection, basically, and inline hooking to accomplish the same types of process monitoring without having to be a debugger or without having to be in the kernel. So here's a really awkward looking graph of kind of an idea of what kernel level monitoring looks like if you're kind of unfamiliar with this stuff. So we have a user mode process. Let me see if my laser actually flashes. Nope, completely useless. Okay. So we have a user mode process. Let's say it calls a Win32 system call called create file. Create file is used to create a file. It's also used to open a file. You can thank Microsoft for that one. That's implemented within kernel32.dll. But just as an example here, any kind of user mode, or any kind of DLL is going to be all accessible within the user mode process. That's going to perform an actual system call, and the way that system call's distributed in the kernel to actually process the request usually goes through this SSDT, System Service Descriptor Table. I'm not going to go into the whole details there. What we're interested in is with kernel level monitoring, such as with process monitor from sysinternals, it typically involves inserting their own device driver that kind of layers on top of that and intercepts the call to, in this example, like ZW create file is the actual system call that happens whenever you perform the create file. Oop, I have it. Oh, yeah, it's too late. So disadvantages here are, well, the advantages is whenever you sit in the kernel, you are definitely capturing every single system call. It's pretty easy to have 100% coverage on system calls operating in the kernel, because you just simply trap everything and you're good to go. As long as you don't have a buggy device driver, there's no real problem with the tool. And I say can't be avoided from user land. That's not to say it can't be detected from user land. So there's really no easy user land way to pick a different routine inside the kernel to process a system call. You don't have that level of access. User processors are kind of forced to use the system calls provided. Now you could certainly install another device driver and do all that. I'm just talking about normal processes here. Disadvantages, you can only capture functions that are implemented as system calls. So nothing that process monitor catches is not a system call. It only monitors those system calls. So if we had a call to, like, for example, get proc address, which is something you might want to observe if you're doing some malware analysis and see what functions the binary is looking up, you're not going to see that from process monitor because it's not a system call. That's implemented completely in user land. And a significant portion of the Win32 API is not implemented as system calls. You just have I don't know, maybe half or so. I haven't done any statistics or so. And the tools do not differentiate between the housekeeping code. There's a lot of things that happen when you start a process that just have to happen just for the sheer fact that you are starting a process. If you've ever run Process Monitor and started Notepad, there's thousands and thousands of events that are taking place just for launching Notepad. There's every DLL, there has to be a create file and has to map that into memory. There's language support stuff that has to happen. There's even really weird things like seeding the random number generator and the prefetch. All those, from the process monitor perspective, those are happening on behalf of that process. So you're going to see them listed in the same level of significance as the actual system calls are happening because that's what the malware author intended. We'll see this when I actually pull up Process Monitor. I'm going to pull up Process Monitor on like Notepad in a bit, and you'll see thousands of events happening for no reason. Well, not really no reason, but you get the idea. And calls to internal DLLs can't be observed, so we're only limited to things that are implemented as system calls. If we had a piece of malware that loaded, malware.dll, and then it started using functions from that, we don't have any way to observe the API calls to its own DLL, whereas with other techniques, we do. Here's a screenshot of Process Monitor in case you've never seen it. I will bring it up in a bit and we'll see it compared and contrast with the tool I'm going to run. But basically, this is just notepad.exe running, and you see down at the bottom left, it says it's currently showing 793 out of 132,000 events. All I did here was just launch Notepad. I didn't do anything with it. And yet you, the reverse engineer, are now presented with almost 1,000 events with which you must sort through and filter and try to get down to something manageable. Not to say it's impossible, but it'd be nice if we had a better approach from the get-go. And one of the problems with this view is it doesn't, there's no way to really filter it to say only show me the calls that are coming directly from notepad.exe itself. So let's say you call load library, which will load a DLL in the Windows operating system. Load library is also going to have to do things like call create file to actually get a handle to the file, then map it into memory and such. You're going to actually see the calls to create file and so on and so forth, in addition to everything else it has to do to get that DLL loaded. At no point are you going to see a nice, simple, succinct call to load library listed as one line item. So that's what I'm trying to work towards with inline hooking. Process monitor via debugging. You can get the same types of information I'm going to be talking about that I've implemented with inline hooking. You can get the same types of things going with debugging. It's certainly a lot easier. You just trap function calls with a breakpoint and stop on the breakpoint and do whatever you got to do. The only disadvantages is, once again, you're acting as a debugger, and if you're willing to take that risk and fight that fight and put up with all that BS, then go nuts. But I'm just going to present a whole other technique that you can kind of skirt on the outside edges and not have to really fight with all that anti-debugger stuff. And I've chosen inline hooks. There's lots of different types of hooks, which I actually don't have a slide for or anything. You can actually just patch the import or the export table of various DLLs and such. I've chosen inline hooks because going forward with the tool, it'll give me more flexibility, so I can potentially hook things that aren't even exported functions. Internal functions you can hook and such No device driver required, not operating as a debugger. The only disadvantages really is, well, besides, slightly not officially supported way of doing anything, is it's kind of a pain in the ass to implement. And we'll go through some of the implementation I have for the tool. And hopefully you'll at least sympathize with my pain. And trapped calls are likely to be highly relevant to the program's operation. This is because mainly, at least in my tool, I've implemented filtering so I can filter just for calls that are originating from the executable. So I'm not getting recursive calls. So if you call load library, I'm not going to report back to you that it's called create file and that it's called map view of section and all that crap. I'm just going to tell you, hey, they called load library, and that's it. So we're going to get that information whittled down for you. And here's kind of what that looks like, same kind of graph as before, except now we're actually hooked up there in the user level as opposed to in the kernel. And the idea is when you call create file with a hook, instead of directly calling the kernel 32 or NTDLL or whatever DLL, you're actually going to call my stuff first, inadvertently. And you might have heard of hooks if you guys are experienced at all with security. Very popular, like rootkit technique and just general malware technique. You can hook things to make a user level rootkit. So if you hooked create file, you can potentially intercept and see, well, if they're going to try an open handle to my malware, then don't let them, or so on and so forth. Or like if you can hook the send function from the WinSock library, then you could potentially, intercept, let's say, emails and tack on your own email address to the email header going out and get a copy of all the emails. Very simple stuff. Fairly easy to implement from a malware perspective because they don't have to worry about all the different stuff that I have to worry about in providing a very general solution that's scriptable. So the basic idea here is we want to find a function of interest and typically disassemble the beginning of the function. Now you can do that disassembly half-ass and just have a kind of a checklist of bad instructions that are going to be too short. I've taken the technique of implementing a full disassembler in the DLL that I inject so I can make sure I'm going to have a very precise count of how much instructions I have to work with so I can know I'm not overwriting something I shouldn't be. So we want to disassemble the beginning of the function for the purpose of we're going to be overwriting the instructions at that function with a jump or a call instruction. Classically, you're going to see jumps more often. If you're just wanting to hook one thing, no problem putting a jump there. It's very easy to do. I've had to use a call instruction, and I'll get to the reasons why in a bit. And you need to implement a handler for the hooked function. So your jump or call instruction needs to jump back to something that you have in memory, which is not a big deal. Why disassemble? Here's a few bytes of a function here. We have an XOR EAX, and a return. That's only 3 bytes. Let's say that's the entire function. This is just a function which doesn't take any arguments and just returns 0 all the time. So it's essentially like a stub. If I tried to overwrite this with a 5-byte hook, if I try to overwrite this with a 5-byte hook, then I've actually overwritten 2 bytes past the end of the function. I don't have any good guarantee on what the hell I've just overwritten. It could be data, it could be another function. So the whole point of disassembling is just to make sure that we're not going to go crazy and that 5 bytes that we need is actually going to be completely contained within this function. Here's a bit more of a real-world example of a function disassembled. This is the function prologue up at the top. We have the push EBP, the move, the subtract, and so on and so forth. You're going to see a lot of functions with this exact sequence at the very beginning. And here I've installed a jump to another handler. And you can see we've just replaced those first 5 bytes with the jump instruction. The next 4 bytes say they're completely unused. This 4 right here. So they're the exact same 4 bytes that were up in that subtract instruction, but now they're just essentially skipped over because theoretically my handler is it's either doing what this overwrote or it's going to jump back here, or it's just going to not jump back here at all and do its own thing. Who knows? If it was nice, it would do this and jump back here. But so anyway. So this is a well-installed hook. It overwrote. It didn't go past the end of the function, and you can only really tell that if you had disassembler when you installed the hook. A lot of malware, though, doesn't really care. They know that like create file is going to have enough space because they've never seen an implementation that doesn't have enough space, so they just go ahead and overwrite it. For a generic solution, though, you need to disassemble. All right, so what do you do once you're hooked? So in this case, that jump, where it said jump to the handler, what do you do? I use the terminology inspect and intercept. I don't know, you can use any terminology you want. I don't really care, but the tool uses this terminology. So inspect would be, I just want to collect data about the current function that we've just called. So if you want to examine the stack, get the arguments to the function, or you just want to look at anything in the process memory, when this happened, take a look at the environment, that kind of stuff. I just want to get a feel for the environment, and once I'm done doing all that, then I want to let the function continue executing after my hook handler has done its thing. With intercept, though, we want to perform an action instead of calling the original function. This is where we get into like doing the sandboxing. So if you're doing sandboxing and they call create file, you want to do your own create file routine. You don't ever want to pass it back to the actual operating system. Oh. Right. So that's where I think a lot of times when you see the hooks implemented in malware, they know exactly what instructions are there. So they can basically know exactly what offset to jump back to or what relative address in that binary to jump back to, if they do indeed want to jump back at all. In my tool, what I do is I use the disassembly information to know. So I did the jump there, and I knew that I overwrote a portion of the subtract instruction, and I know that the XOR instruction is the next instruction that it did not overwrite. So when I install the hook, I actually copy the instructions that I overwrote out somewhere else, and I basically redo that functionality, and then that tails with a jump back to the XOR, ECX, ECX. Oh, I'm sorry. The question was, how do you know that once your handler is finished operating, how do you know you're not going to just jump back into the middle of another instruction? And to which I said, well, you kind of have to use the disassembly information to know what the next instruction was that you didn't overwrite a portion of. And in my tool, what I do is I take the instructions that I did overwrite and I redo that functionality before jumping back. So I actually just copy them verbatim. I make sure I'm not copying anything that's position dependent and then it needs to be relocated. I just kind of fail out currently and say I can't install a hook here. In the future, it'd be nice to support that, even that case. But does that cover you? Okay. Like I said, malware normally does it very cheaply. They just blast it in there. It's very easy to do. If you just, I want to hook one function. I know exactly where to do it. I know exactly where to jump back. There's no big deal to it. All right, so getting into rolling your own sandbox. So once you have these hooks, it can really be up to you what you want to do with it. As long as you're maintaining the stack appropriately when you return back to the function that called it, you can do anything you want. So here's some ideas on how to implement some rudimentary sandboxing, and I have some examples of this in the modules that I have for the tool. So for example, if you just put a hook at get host by name, you can just always return a fixed IP address. That gets you a very rudimentary DNS trapping. We currently use like tools to do the DNS trapping, like set up a little DNS server on your box and point your DNS settings to yourself. But if you're operating within the process like this, you don't even need to have a DNS server. You can just always return a fixed address. Same thing with like create file, read file, write file. If you wanted to sandbox those away, you could just make like a pseudo handle interface. So you return a handle that has some unique value to you, and anytime you see a read or write file go to that handle, you know that that's something that needs to be sandboxed instead of actually passed off. Same thing with, you potentially do that with sockets. I haven't actually implemented of these yet. I have an implementation of the get host by name because it was a fairly easy one to do. So why I started thinking about this inline hooking stuff and why I'm going down this path at all is I personally use this a lot for malware analysis, particularly when you get binaries that are really protected with anti-debugging stuff very heavily, particularly in the form of a packer. I'm not saying I need to do this for every packer, but every now and then there's one that's just a real pain in the ass. So instead of taking my time and beating through it like I should, and with a debugger and trying to counter all their techniques, I typically in the past have just used inline hooking to dump it very quickly. So this technique, I've never seen it documented, so I'm just going to document it here in 2 slides and let you know my little technique. This is all completely manual. Eventually this will be in the tool as well, because this can work completely just in memory. So the first step I would do to install inline hooks for the purpose of unpacking is disable known DLLs. Basically, if your process asks for kernel 32, it's always going to go to the fixed location. It's not going to follow the normal DLL search path, as long as you have this known DLLs key turned on and that's listed in there. So you have to first turn that off, and my malware environment that I operate in has this turned off, so it's very easy for me to do. Then copy kernel 32 to the directory with your packed binary. So now, when you launch that binary, it's actually going to take that local copy of kernel 32 instead of the actual system's kernel 32. Because you can't easily modify the kernel 32 in the system. You need to turn off file protection and yada yada. So it's easier just to work with the local copy. Then you need to find a function you can pretty much guarantee is going to be used only in the unpacked code. So if I chose create file, that's not a good deal because there might be something going on in the packer routine or just in that like process startup code that calls create file, and that's something I don't want to do. But write file is not normally a system call that happens just by the sheer fact of loading a process. They don't normally write data. Git command line, potentially. You have to use some creativity, and this is going to vary from case to case. Not all binaries are going to call write file. So, but write files had pretty good success for me in the past. So once I pick out a function that I want to trap, I find the location within the file of that actual function. I'm going to omit the actual steps to do the conversion, but you need to figure out where that function is in the file. And go to the first 2 bytes of the function and replace it with an infinite loop. This is basically installing your own little inline hook that's just a trap. It's only 2 bytes, so basically every function you're going to be able to trap in this fashion. So whenever that function call gets called by that binary, it's going to go into an infinite loop. You're going to see the CPU spike, and it's going to be basically hung in memory. This is which is for unpacking malware. It's exactly what we want. We want to get the malware in a place where it's unpacked and it's just sitting there waiting to be dumped. Question? Right, but the question was, what happens when the malware copies itself to another location and it's out, and it then doesn't have that modified copy of kernel 32? Typically, the copying behavior is going to be code that the actual programmer implemented in his malware, not part of the packer. So when it actually gets to the point of doing the copy, it's probably unpacked in memory at that point. So we can still trap it on write file or copy file or whatever. And it's going to get it when it's unpacked before it's actually done that copy. So it still works. So. Yeah, the actual techniques I'm going to use, it's all going to be in memory. It's not actually going to require this modified copy of kernel 32 to be local. So even if you potentially the malware spawned off another copy of itself, the current tool doesn't trace that. It's not going to attach to the process it copied. Potentially down the road, yes. I'm just kind of giving you some history on here and why I'm going down this path of inline hooking in the first place, and some practical usage of it. We can get more on that offline. So anyway, once you have that hook installed, all you got to do is launch the binary, and then you'll see the CPU spike, and you just dump process memory using basically any technique at that point. It should all be good. This is If I don't easily unpack it in a debugger, this is pretty much what I do most of the time. I get just about everything unpacked very quickly. So at first, before I started writing this tool, I was just thinking I was just going to write a tool to basically do that, but operating solely in memory, like inject a DLL into the process and hook write file or hook a bunch of other things, just so that they would spin. But then I was thinking, well, if I'm going to write a tool to hook stuff, why don't I just go ahead and write a tool to hook stuff and monitor it and let you play with it and screw it up? So that's essentially the route that I went down. All right. So the tool I wrote is called API Thief. There's lots of better names potentially for it, but they were all taken, so API Thief was the best name I could find that wasn't already taken. Searching on SourceForge and all that. Anyway. So how it works is it launches the target process in a suspended state, and it injects a DLL into it using just basic process injection. That injected DLL, first it runs through and looks at all the loaded modules and kind of maps them out. And it's this loaded DLL that does all the disassembly, does all the hook installation. It also is responsible for handling all the hooked function calls. So everything's going to kind of point back to here once it's been called. And then there's a GUI portion of it, which has a kind of a process monitor style console that lets you get the events. You might be aware that iDefense had a kind of similar tool that did this sort of thing. It did use inline hooking, and it did attempt to trap system calls. It was just, the way it operated though was just a fixed set of functions. It had a list of, like, I figured maybe 20 functions, and it just installed a very simple jump hook, and each one of them had their own handler, and it piped the output over a socket back to the controller. The tool had some issues, wasn't very user-friendly. I never ended up using it much in actual malware analysis because it was just hard to work with. I actually figured that out after I started writing the tool. Anyway. And this particular tool, we have an embedded Python, actually Iron Python, so it's all, the actual GUI is in C#. So you can have Python running, and Python's actually going to be the component that figures out whether or not it should hook a function, and if it does hook a function, what it's going to do with it. And this is all stuff you can play with and modify and implement. So there's the injectable DLL that's written in C with a whole bunch of inline assembler. And that has the disassembler built in it. The GUI, like I said, is written in C#. It currently targets the .NET Framework 3.5. I can probably ratchet that down if anybody has serious objections to, like, 2.0 maybe. And of course, embedded Iron Python. So just be aware that if you are going to start looking into writing Python scripts for this, it's not going to actually be the same Python environment that's installed on your system. It's its own deal. Think of it more as an extension language for the program specifically. I do have the whole Python libraries in there though, so you can do everything you need within reason. And in terms of hook methodology, I differ from a lot of other tools in that I install hooks with a call instruction instead of a jump. The reason is we have a single dispatcher, so the second bullet there, all hooks point back to the same dispatcher. This is so we can support an arbitrary number of hooks. Most other tools that do inline hooking, they hook a specific number of functions. Each one of them they have their own little hook handler for. That's good for your kind of really basic approach, but if you don't know how many functions you're going to be hooking, you need to be very flexible and potentially changing it runtime. You kind of need to have a more generic approach. So by installing a call, I can point everything back to the same dispatcher, and if you remember right, the call instruction pushes a return pointer on the stack. Therefore, I can use that return pointer to know what function I actually came from. So if they called create file, and then create file does a call to me, the return pointer from create file is going to be different than a return pointer from, write file. They're going to be different addresses where that hook was installed. So basically, we have a way to map back from the hooked function to what we need to do once our hook processor is finished or while it's working. So I use a call instead of a jump. Of course, there's some stack issues that come in with that, no big deal. It operates currently over named pipes back to the GUI. Potentially I can move that to sockets later on down the line. Just I did it all local for now. Okay, so the question was, how do I prevent my own handler from calling back a hooked function and then perhaps getting into like an infinite loop of, that's where the filters come in. So I do filtering based on that return pointer, actually based on the return pointer that first called the API function. So if you call from, notepad.exe, you call create file, I can tell that that return pointer is coming from Notepad. Right. Yeah, so if it comes from myself, or actually, if it comes from currently I don't have it configurable, so currently if it comes from anything but the executable module, I just don't process the hook at all. So I'm only capturing hooks just from the executable, which is, at least to start out with, the best way that I can use to get down to just the most important system calls.
How does that handle hackers that copy stuff to virtual memory?
It doesn't hook, you're not going to get any hook then from that virtual memory to start out with. You can potentially script it though with Python, because you'll be able to catch when it does the alloc for the virtual memory, you can catch that and potentially, expand your filter to trap anything that comes from that range. I don't have the filters scriptable yet. That'll be later on down the line. So the Python layer is the one that does all the logic on whether or not it should handle hooks, what it does when it gets a hook, you get all that stuff. Yeah, I told you there'd be assembly code in the slides. Just some academia on how it actually does what it does. So this is a little snippet from the code where it actually does the interception. So if you actually decide I want to do some functionality instead of doing what the actual system call was, there's some interesting things you've got to do to get that to actually work. So here in the call instruction up there, that's where I actually start interacting with the remote process to actually do that's where it gets the commands to what it wants to read, what it wants to write, what it wants to replace. Some of these functions though that you can do from the GUI is actually you can set the return value of the function, because I have the EAX register saved on the stack. So one of the commands, you can basically supply it a new EAX value, and then the series of the process inspection command that actually processes that will actually overwrite it directly on the stack. So here's where the pop EAX happens. So when it does that pop EAX has already been poisoned with whatever value you supplied remotely. Same deal with, if you're thinking, the only real issue with doing inspection is if you have standard call. Standard call functions are basically responsible for removing the space for the parameters to the function. So if you had a function that takes 2 arguments, that function has to do like a return 8 so that it subtracts off those values off the stack. So that kind of complicates things, because if we trap a standard call function, we have to know how many parameters that took, and we have to adjust the stack ourselves manually. So I just kind of threw this up here. This is the code where it's actually doing that. So it's kind of a very complicated way you have to exit the function, because there's no return instruction which will return a variable number of a variable amount. You can't subtract a variable amount. There has to be fixed numbers that you're doing the return instruction for. So the last line there is what's actually doing the return. It's kind of complicated. I'm not going to go into it step by step. And the very beginning of this is the dispatcher function that gets called every time a hook gets called. If you notice some of the things it's doing here, the only 2 lines I want you to look at is where it saves off the function pointer, then saves off the caller. The caller is where that's the pointer that the original call to the API call was made. So if they call create file, that return pointer pushed on the stack at that point is going to be caller. And function pointer, since I installed the hook that's a call, that's going to identify that as a unique function. So based on the value of that function pointer right there, I'll know which API call I'm currently intercepting. Anyway. There's a whole protocol to it. Like I said, other tools, what they did is just blindly write data across a socket, and hopefully that the other end just kind of gets it and displays it in a certain way. Personally, I didn't want any of the display information or anything really, any intelligence inside the DLL that I inject. I also wanted it to be more thread safe. So if you have 2 threads in a process and they're both hooked and they both start writing a whole bunch of data, the data is going to start clobbering each other. So I implemented a whole protocol so that once you've called a hook function, the rest of the process basically gets locked, waiting on a mutex. So you can interact with that function, intercept the function, play with its data, and you can do that at your leisure. It's not going to continue anything else until it's actually finished. Yeah, so you can get an idea of some of the things you can do. You can get a module list straight from there. You can get the value of ESP when the function was called. That's how we're going to actually look up the function parameters. You can get the FS register. You guys know all the things you can do with the FS register in Windows. It's an important component. You can set the EAX register. That's what comes down to setting the return value of the function. You can set the parameter size. That's in case you call a standard call function. And you can do a load library, because basically you need something special to trap load library if you want to actually traverse it. It's just an example of the protocol. I'm not going to go into it in too much depth. So you get a request from a hook call, and the GUI console tells it whether or not to intercept or inspect or whatever. And there's a bunch of these success messages that get passed back. The success messages will actually carry data payloads. So if they say get ESP, for example, the success packet is actually going to contain the ESP value in kind of a data payload for it. And then once he got the value of ESP, he says set EAX, because he's doing an interception. He wants to set a return value. That gets handled by the hook process, sets the param size, and then he tells it to continue. That's going to allow the actual original function to continue. Or actually, in this case, it'll go back to the original program. All right. Quick peek at the API for plugin development. There's really not that many functions. You don't really need that much to interact with the other process. You need functions to tell it whether or not, once you have a hooked function, whether or not you want to inspect it or intercept it. So if you're going to do a sandbox or just observe some stuff. Continue. Once you've done doing whatever you need to do, you can let the process continue. Report. This is how you're going to get information back to the GUI console. Get args. These are kind of wrappers to let you easily access arguments to the function. And I have some wrappers here for reading ASCII and Unicode strings. Set param size. This will set the amount of parameters to the function. In case you called a standard call function, you need to adjust that appropriately. Set return value. That's going to overwrite that EAX value. And of course, you have alloc read and write. So if you have alloc read and write, and you can set the return value, and you can fix the stack on function exit. That's basically, from a low-level programming perspective, that's all you need to do to implement sandboxing. You have the ability to completely do anything you need in this process. Cool. So here's an example of, actually this is a complete plugin right here for a hook on beep. This is actually an intercept, so beep will never get called. This will get called. Here I'm not a Python expert, by the way. I probably know very minimally, so if there's something stupid in here, don't complain to me. Well, maybe complain to me, maybe I'll fix it. So we register the hook up front. Once the hook gets called, you see I registered it for the handle beep function down there. So that's actually what's going to process the beep function, not the actual kernel 32 beep function. It's actually going to go through these series of steps. One of the steps is I'm reporting information about the beep function back to the GUI, and I set a return value. Oh, actually that needs to be fixed. Well, yeah, I kind of condensed some stuff for the slide there, but so I can set the return value to anything I want. In this case, it's set to something that doesn't exist, but you get the idea. Beep takes 2 arguments, so that's why I have the set param size down there of 8. Oh, well, this is a little bit easier. Big. Set param size 8, so I can make sure that those 2 parameters to the beep function call get adjusted when the function returns. So it's pretty easy to do trapping. You can see it's just a couple lines of Python and you're good to go. Here's the GitHost by name sandbox. So this Python module is included in the package I have up on the net. You can see it's really not much to it to actually return your own data for the GitHost by name call. I do like a read ASCII string and a report just for the sake of reporting that back up to the GUI console so you can see what host name they were trying to access. If you're doing malware analysis, that's very important. But then I alloc space for it, and then I do a write to write. This is 127.0.0.1. So any DNS request is going to get the value 127.0.0.1. Actually. Woot. Was that? Yeah, it's mine. Yeah. There's a plugins directory right here that has those couple plugins that come with it. The plugin framework itself, though, is all written in Python as well. So if you didn't like the way I'm doing plugins, you can completely change all that. Let me also pull up. Let me pull up Process Monitor while we're doing this. All right, so here's API Thief. Oh crap, I didn't change that. Oh well. So let me go ahead and load up a process so we can see. Here's I'm going to start with test API Thief. This is a little quick binary. It only does a couple things, just so we can see it working in a very simple fashion. Here you have a list of plugins. Like I said, I only have 3 Python files in there right now, so that's all we have. There's a basic Win32 API monitor that just does inspect on most of the important Win32 API functions. A load library hook. If you have to hook a function which is going to be called via the load library at runtime, go ahead and use this plugin, because then I have a wrapper for load library that explores the modules. In this example, we don't need that though. And we have a get host by name trap, which is that module I was talking about in the slide. So first, you select the binary, which I did with this little, the dot, dot, dot. This is actually the command line window, so if it took parameters, you could pass them right here. And then we say initialize. The initialize is going to start the process suspended and inject that DLL, and the DLL, once it starts, it's going to run through and start hooking a bunch of stuff and reporting information back. So this already reported information back. You can see I have a list of the modules. This is information coming out of that process via our named pipe in the background. I have a few other windows here. I can see the list of things that I currently have hooked. So kernel 32 has all these hooks. I apologize, they're not in alphabetical order. And WinSock 32, here it's that get host by name hook we have. If you notice the icon by get host by name has a little script, that's because that's an intercept. And these are inspects. So you have a magnifying glass if you're just inspecting. If you have the script, it's actually intercepting. Speaking of script, there's a little script window. Not the most useful thing right now, but it is the same Python environment that's doing all the plugin stuff. So I can say, and execute that. Oops. And of course that didn't work. Anyway, I went ahead and hit launch. I don't know what the deal, oh, I think now it'll work. Anyway, so I went ahead and hit launch, and it had those few things trapped. And you can see in the output, of course my output isn't all that pretty right now, but we can see a call to get system time is file time, a call to load library PS API, a call to create file, a call to beep, and a call to sleep with some big value. This is really all this little C program did. Whereas, oh no, I forgot to turn on process monitor. Let me go ahead and turn on process monitor, let it start. Yeah. We're going to redo this. We're going to compare the process monitor output with API Thief's output. Turn on that trap. Initialized it, and I'll launch it. So that's all we have in here for this little test program, but you can see in Process Monitor, we have a lot more. We have 970 events, and it's kind of hard to see that exact information about beep and load library. You can go through here and do some filtering and hopefully try to catch some of it, but in general, this is just a lot more information to go through. Let me see if that script works now. There it is, yeah. So that popped up, hi, black hat, whatever. Oops. Do a couple more just so you can see it wasn't like a rigged demo or anything. It does take a second to start. I think it's all the Python stuff. IronPython's a bit of a pig. All right. I'm going to go ahead and load up Notepad. I did get host by name trap on Notepad, but there's no get host by name in Notepad, by the way. All right, I went ahead and launched it. That's a little bit odd. I don't know what's going on there, but you can see we have I'm only trapping kernel 32 currently in this little module. It really isn't all that well fleshed out, but you can see that it actually works. So I can see I have get calls to get proc address. That's certainly information I don't see in procmon. I have calls to, sorry it's a little bit small. Even I've also trapped like the string compare functions within kernel 32, and I even see those getting called, which is certainly something you would never see in procmon. Oops. So I just saved test.txt, and sure enough down there we see see it calling find first file. That's another thing you don't see in process monitor. And there's the create file call, create file W, and write file, set into file. You get the idea. That's really about it for now. Am I doing on time? Which one more? Click launch. And this was a packed binary, and you can see the unpacker stub. It goes through and does the load library and all the imports, and does get proc address to repopulate that import address table. And we can see that going on here, just from a hooking perspective. We see all that information. So that's really about it. Oops. All right, so the proof of concept code, if you want to go download it, it's on my site, which is rnicrosoft.net. That's not an M. In the future, it'll be at my company's website, mandiant.com, and you can get a hold of me, Nick Harbour, or at Mandiant or Gmail. With that being said, that's about all I got. Any questions? It'll be free, yeah. I mean, it's free right now, but it'll always be free. So, other question? As opposed to what? Yeah, I believe the detours requires you to run against the actual binaries. They don't have a fully in-memory capability that I'm aware of. So this tool, you just pass it a binary, and all of its hooking is done just within memory, as opposed. Oh, yeah, I haven't actually looked at detours package since like 2 years ago. But when I did, I remember it's primarily supported to extend the functionality by actually modifying the executables. They don't have like a full hooking, at least at the time, they didn't have a full hooking solution completely in memory. So that was my impetus for doing it the hard way. Anybody else? Yeah, any DLL will work. So I just did kernel 32 because that's the most bang for the buck for malware analysis. That Python, actually I can pull up the script that actually did that, and you can see how easy it is to look at what I did. So in this particular one, I just wrote this all myself to do the hooking of these, and I just say hook kernel 32 beep, and it takes 2 ints that I want to print out in decimal notation. Like I could change this to be user 32 colon, get clipboard, whatever. Doesn't care. As long as you're just inspecting, you don't really need all that much information about the target function. That'll be up to your Python code. So from the stacks perspective, all arguments to the function are just D words. So you can figure out the D word, and if you're writing a handler for that function, and you know that argument is a pointer to a struct, then you can go dereference that memory. If you remember right, I provide calls to do reads and writes and Alex, and even interpret strings automatically. So it'd be up to you in the handler to write that. I mean, eventually I'm going to try and fully support as much of the Win32 API as I can. This is just the first draft, really. So I'm not doing any structure interpretation. Question? On Linux with Mono? Pretty difficult because I'm using like Windows process injection techniques to get that DLL loaded. If you can find me an easy equivalent to create remote thread on Linux, that would be great. It's much more difficult. You have to like ptrace and inject that way, in which case you're basically a debugger, and that defeats the whole purpose of not acting as a debugger. So yeah, I'm not even considering that right now. The vast majority of malware we get at our company is all Windows, so yeah, pretty much, probably just about every company, but I'm pretty much going to be Windows focused for the indefinite future. Yeah. So, but I don't know. Any other questions? Alrighty. Thank you for your time.